My name is Kenya Pujols, and I am the COVID Information Commons Program Manager at Columbia University. I am really excited to be here today with also our Executive Director, Florence Hudson. So I'm going to begin briefly introducing you to our COVID Information Commons program before I introduce you to Florence Hudson and our speakers. So the COVID Information Commons, or KIC, how we call it, is a COVID-19 research collaboration platform to facilitate knowledge sharing and collaboration across various COVID-19 research efforts. We now have 1,816 NSF awards on the KIP database, and we're planning to add thousands of NIH awards this year. Every month, the KIC brings together scholars from all over the country to share their research findings in the form of lightning talks. Each scholar will also engage the community directly, answering questions about their work during the Q&A section at the end of the presentations. We are very happy to announce as well that the KIC community includes 1,970 individuals representing more than 600 institutions. Additionally, since July 2020, we have hosted 18 webinars, in total 96 talks, and we have accumulated more than 6,000 views with the live attendees and the YouTube channel. And with the help of our students and volunteers, all the 96 KIP Lightning Talks have been transcribed to English, and they have been shared on the KIP website. 70 of those are also available in the library, the Columbia Academic Commons. 29 of those as well has been translated to Spanish, and they are available on the KIP website and the Hub YouTube channel. So before we continue with the agenda of today's agenda, I would like to introduce our Executive Director, Florence Hudson, to share some words with us.
That's wonderful. Thank you, Kenya. If you could go back one slide, please, to the KIC homepage, that would be great. Thank you. And thank you, everyone, for being with us today. As you could see in the numbers that Kenya just showed, we usually have 5 times as many people that actually review these webinars afterward. And we know that today is actually a religious holiday for some people. And so we're sorry for those who can't join us live, but I know a lot of people wanted to look afterward at it as well. So the COVID Information Commons began in 2020 when COVID-19 was spreading around the world and became a pandemic. And the National Science Foundation asked us at the Northeast Hub to work with the other big data hubs around the country. There are 4. And to work together to create the COVID Information Commons to find a place for people to easily identify and learn more about NSF-funded COVID research. So we started that. At the time, there were only 32 COVID Rapid Awards in March of 2020. And now, as you heard from Kenya, there are over 1,800. So we created this capability, and the KIC is an open portal as well as it became a community. We had our kickoff meeting in July of 2020. We had over 170 people come, which we were really surprised about. And we had over 40 researchers, NSF-funded principal investigators, request to present. So we said, well, we can't fit you all in one webinar, so let's create a series. And so it continues. And now, as Kenya said, we have already been inviting NIH, AHRQ, and CDC PIs to present, but we're going to be also adding those NIH awards and those others into the COVID Info Commons portal. So you'll be able to easily identify research in particular areas across those funding agencies. In the KIC, we have these search tools. We have a machine learning explorer-based tool, which gives you clustered maps of the different research areas. And then we also have Meet the Researchers page. So each of the PIs or researchers who are presenting today, we will have them in the webinar recording that is available clicking through the KIC and also on YouTube, and we'll actually have separate videos of their particular video, their tutorial, their lightning talk. So if someone's just looking for what Murat is talking about, in 10 minutes, they could actually just go watch that one. And that's where we're putting the English transcripts. You can click through to the English transcripts there and the Spanish translations. And I really want to thank Kenya, who just joined us at the end of January as our COVID Info Commons program manager, for leading the Spanish translation effort support along with one of the students on our team, Isabella, and then our operations communications manager leading the overall English transcription. And we'll continue this into the future to improve accessibility of this information for those who may be hard of hearing and can't listen to the video, and those who speak Spanish and would like to listen to it or read it first in Spanish. So there are many resources under opportunities and resources at the COVID Info Commons website. We have over 50 data sets from around the world, and that continues to grow. And with the extension of the COVID Info Commons from the original grant we got from NSF, which we're very grateful for, in 2020, in 2021, we got our extension grant, which is for four more years. And we're going to be adding some new search, metadata and data search and discovery mechanisms. So you can put in a keyword and find information in multiple places that's well vetted. So we encourage you to use this, share it with your friends, your students, your family around the world. It's open and live all the time, thank goodness. And we're very grateful Columbia University helping to host it as well. So that's what I want to tell you about the KIC. We're looking forward to the future. We're going to be doing a demo of the new integrated NSF NIH platform in a couple of months. And then we're planning a workshop, a comprehensive workshop at the end of this year, and a new student paper challenge. We had one last year that was just undergraduate, and we're planning to have a new one that's for community college undergraduate and graduate students. And we're super excited about that. That will be announced probably this summer. So with that, we're just delighted to have everybody here. We want to thank the participants. We want to thank all the presenters, and thank you for all the research that you're doing to combat COVID. Thank you, Kenya.
Thank you very much, Florence, for those words about the KIC. And before I introduce you to today's speakers, I would like to also thank Benji Sanjo, who is a Columbia student, and he is joining us today, and he's helping us with the webinar. So that being said, let me introduce you to today's speakers. So the speakers that we invite, they going to be discussing topics about the supply and demand change and privacy and security during the COVID-19 pandemic. As you know, this has been a very important topics that have been negatively impacting healthcare workers, and also once we transition to working from home or studying from home, data sharing has been a main issue. So today's speakers include Justin Boudelier from the University of Wisconsin-Madison, Kaiming Yi from SUNY Binghamton, Murat Kantarcioglu from University of Texas at Dallas, and Zachary from Brigham Young University. So I'm gonna stop sharing, and I'm going to invite first Justin Boudelier. If you can please begin your talk and share your screen, that would be great.
Thank you very much for the introduction, and welcome everyone who's here this afternoon. So my name is Justin Boudelier. I'm an assistant professor in the Department of Industrial and Systems Engineering at UW-Madison, and I'm going to be presenting some work titled Shieldnet, Matching Face Shields During COVID-19. And this project is a collaboration between myself, Professor Oyan Sadiq from UCLA, and Rebecca Alcock, who is a PhD student in my lab here at UW-Madison, and she was the lead on this project. So for some context about the problem, the COVID-19 pandemic, as many of us know, led to unprecedented and widespread supply chain disruptions. And one very acute area where these disruptions were particularly impactful was PPE. And within the first month of the pandemic, the United States had actually used over 90% of the strategic national stockpile of PPE. And in response to this shortage of PPE, there were new strategies put out by medical practitioners for rationing and reusing existing PPE that we do have. And we know now that many of these strategies and shortages put first responders and healthcare workers at increased risk of infection. And there's been several studies that have followed up showing the magnitude of this increased risk. And, at the time when this was happening, this was quite popular in the mainstream media. And there were two, very famous hashtags, which is "Where's my PPE" and "Get me PPE," try to bring people together and get PPE into the hands of healthcare workers. And at the same time as we were experiencing these supply chain disruptions and shortages in PPE, we were also experiencing closures of non-essential businesses. And this led to a surplus of manufacturing capacity in other industries. And so we call this, or we coined this, a pop-up supply chain. And effectively what a pop-up supply chain is, it's when a non-traditional manufacturer pivots its production processes from whatever they used to produce to producing PPE. Now, certain types of PPE, especially face shields, which are quite simple to produce, are very well suited to something like a pop-up supply chain, because almost anyone, whether you're a mom and pop, small manufacturing organization or a very large industrial manufacturer, can pivot their production lines to making face shields. Now, this pop-up PPE supply chain is different from the conventional PPE supply chain in two important ways. And so first, the conventional PPE supply chain is dominated by large players, right? So think 3M, Honeywell, companies like this. And so there's it's challenging to enter this market. It's dominated by a small number of large companies, whereas this pop-up supply chain has very little barriers to entry. And as a result, we see a wide range of manufacturers who enter the market, all the way from very small ones to very large ones. The second big difference is the distribution channels. So traditional PPE supply chains, the products are distributed during disasters in a very formal way, typically through the federal government, the Federal Emergency Management Agency, and then the local, state, or county agencies from there. And this process is effective, but in some cases, it may actually leave behind small medical facilities like dentists or family doctors who aren't quite on the radar of these federal and state emergency management agencies. And so a PPE supply chain has this ability to sell directly to these consumers and create more connections. And then lastly, the biggest challenge perhaps is just procurement. Because many of these manufacturers are new to the marketplace, they're not on the radar of medical facilities, and they may not know how to get in contact with facilities that do need PPE. And so this is where we came in. And so the goal of our project was to develop a platform that could match manufacturers of face shields with requesters, and to collect data on the performance of this platform so we could study its effectiveness as well as its potential, the potential of this type of pop-up supply chain in future disasters. And so we coined our website Shieldnet. This is the landing page of that website, and you'll see there's two buttons here. And so you can click, if you're a manufacturer, I make face shields, or if you are a requester, like a hospital or other medical organization, I need face shields. And based on whichever link you click, you're taken to a supplier or a requester form where we collect some basic information from you, like what your production capacity is, lead times, location, and things like that on the supplier side, as well as information about the size of your request, urgency, and location on the requester side. And we use this information as input to a linear programming model. So this is a prescriptive analytics or optimization model that produces matches every day between requesters and suppliers. And I've given you an idea of what the model does here. Essentially, we prioritize urgent requests and minimize shipping distance. And we have constraints, to make sure that we're not exceeding capacity of suppliers or requesters, as well as keeping track of any shortfall that needs to be carried over from prior days. So without further ado, I'll tell you a bit more about how this actually went and what we learned from this process. So during its operations, Shieldnet produced 390 matches, and these were produced between the middle of March and September 2020. The website was launched the week of March 21st, so not long after the pandemic began. We received over 340 requests from 43 states and Puerto Rico, and we had 373 suppliers join the program from over 40 states. And we followed up. So as Shieldnet produced matches, we followed up with the matches manually and inquired whether or not the match was successful, meaning how much product was actually shipped, if any, what the price was paid for that product, how long it took to get there, and things like, as well as other more qualitative questions like how satisfied they were with the service and whether they would return. We similarly interviewed those who had unsuccessful matches. And then you'll see the gray area here is unclassified. Those were institutions that we just weren't able to follow up with. Either they were too busy or weren't able to get in contact with anyone. And so throughout Shieldnet's operation, we were able to deliver over 50,000 face shields to 68 unique organizations across the country. And then we used this follow-up data to investigate the match success rate of the platform and reasons why the platform might have been successful or unsuccessful. And so overall, our match success rate was 27%, which in the context of other online matching platforms like dating or vacation rental booking or job searching is sort of within the ballpark. And then interestingly, we found that more than half of the unsuccessful matches were able to fulfill orders elsewhere. And many of them told us that they were using Shieldnet as a backup plan, basically, which was good for us. The second thing we learned is that more than half of the successful matches ended up being repeat customers, meaning that those individuals actually ordered shields again from the same manufacturer, but offline from our platform. And we consider that a success because it created the connection that led to procurement of this PPE. And then finally, we looked at what factors may have influenced whether or not a match was successful. And by far, the most significant factor we found was proximity. So the closer the location between the manufacturer and the requester, the more likely they were to have a successful match. And we believe this might be true for a couple of reasons. One, shipping times and lead times would be generally quite short. If that was the case, you could have an in-person delivery, which gives you some, sense of like community and altruism and, actually seeing this person face to face rather than just ordering everything online. So we believe that, played a factor into this. And then I think most interesting to me was that Shieldnet also allowed several suppliers to continue operating during the early economic shutdown from COVID-19. And in fact, this is a quote from one of our manufacturers who said that their transition to PPE production allowed them to keep their regular staff of 40 employees working, as well as hire 8 new additional employees to help with the PPE business that was essentially going well in part because of Shieldnet. And so to us, this was a really great outcome of this project, being able to have 8 additional employees, potentially families, employed during this time is certainly not worth overlooking. And then lastly, I'll give you a sense of some of the broader impacts of this project. And this is in part because my research program focuses primarily on global health projects. And so I have a big interest in international research and international development. And my PhD student, Rebecca, shares these interests and has done prior work with Engineers Without Borders. And so the success of Shieldnet caught their eye and led to a collaboration with Engineers Without Borders here at UW, as well as the United Nations Development Program more broadly. And this engagement led to us, having assistance and playing a small role in community-centered PPE production in 13 different countries around the world. Basically others saw the success of this sort of local, crowdsourced PPE production and felt that they could replicate it in these other locations. So we helped them do this. And the countries with the biggest impact in terms of numbers of PPE being produced were actually Yemen and Kyrgyzstan in Asia. And so that's all I'll say for today. Thank you very much for attending and for listening. Of course, this work was supported by an NSF Rapid grant in the early part of the pandemic, and we have a publication out, which is on screen now, if you're curious to learn more about the work. So thank you very much.
Thank you very much, Justin. This was a great presentation. I'm pretty sure the audience has many questions, and I think I saw some questions popping up in the chat. So please feel free to ask your questions to the speakers. You can answer the questions in the chat, or you can wait until the end for the Q&A section. Whatever you prefer. We might also ask you to repeat the answers to your questions, even if you share in the chat. So next, So next, I would like to invite our next speaker, Kaiming Yi, who is coming from sunny Binghamton. You're free to share your screen. I think you're mute, Kaiming. I believe, your audio.
All right,
yeah.
Tonight should work. Sorry for that. Thank you for the very nice introductions. My name is Kaiming Yi. I'm the distinguished professor in the SUNY Binghamton Universities. I'm also the chair of the department, Biomedical Engineering, also the director of the Center of the Biomanufacturing for Regenerative Medicine. Let me see how I can go. Okay. So this is the NSF funded rapid projects in the very beginning with the COVID pandemic. This is the research team. So it's a collaborative research and between the Binghamton University and also the Arizona State University. And in Binghamton teams included me and also the Dr. Guy German. He is the assistant professor in the Department of Biomedical Engineering, and a PhD student, Sebastian Freeman, and he did all the work. And part of the COVID testing was performed by the Dr. Corin Kibler and Arizona State University. So this is the problem we intend to solve, and with this grant on the award. And in the very early of the pandemic, so we all facing shortage of the PPE, particularly N95 maskers. So we received a lot of requests from the local hospital and also the hospitals and other medical centers. They asked the simple question, is it possible to reuse N95 maskers by some way to disinfecting the virus contaminate the maskers? So we immediately thought about idea using the UVC, that's the UV light, to disinfect the maskers, because we use the UVC all the time and during the cell cultures to disinfect any surface that contaminated by the microorganism or the virus. We designed, I think it's this is the device, where is this thing? Okay. So we designed several devices and then to sterilize to basically disinfect the virus. So the light we use, and based on the UV lights, and if you look at it here, there's a three category of the UV lights, and it's called the UVA, that usually in the very high wavelengths, that's between the 315 to 400 nanometers. And another category of the UV light called a UVB, 280 nanometers to 350 nanometers. Much lower wavelengths of the UV, that's called a UVC light, and between the 100 to 280 nanometers. So this is a category of the lights we are much interested, because and those lights and particularly can destroy the DNA. If you look at these panels, so the DNA RNA, they all have the thymine bases. So they those bases can absorb the UVC light, very short wavelengths of the UVC, and between the 100 to 200 nanometers, then form called the thymine dimers. When those dimer forms, and the DNA RNA will no longer be able to replicate it. In other words, the cell, whatever the cell or virus cannot be replicated. So in that way, the virus will be destroyed because they have no capability of their spreading among the cells and also infect the cells to destroy the cells. So that's the reason the UVC lights, widely known as called the germicidal disinfectants. And because using the lights is very easy and compared to using the chemicals, because we know it, a lot of people thinking about using chemicals to disinfect the surface, or using coating any antivirus chemicals on the surface to disinfect the virus. But light is very easy and very shorter, because usually you can disinfect the surface within minutes. So the study we set up to basically we intend to discover is what is the dose we need to eradicating the virus on the virus contaminated surface. Particularly in the very early on, we designed these devices, we sent these devices to the local hospital, and on a lot of medical centers, they use the system to sterilize reused N95 maskers, without knowing what is the right dose we require to and completely eradicating the virus. But we, in order to reach some efficiencies, we use the extra light intensities. So basically, we use the more intensities than we should use. Now the question is, we ask. That's the reason we talked to the NSF about the idea. Develop the model system, allow us to determine the appropriate dosage, a level of the UVC intensity. Then we can, based on those data, to design the more efficient UVC disinfecting the devices. So this is basically the process. I don't want to go through the entire design process. I just want to show you some results. So we did develop the devices. Basically, this is the homemade devices and allow us to check the intensity of the lights and also the power of the lights needed to in order to completely eradicating the virus on any contaminated surface. Then we use these devices to determine the UVC dose for eradicating the SARS-CoV-2. That's the virus caused the COVID. So during this process, we discover is a very interesting phenomenon. When we suspend the virus in PBS buffer, that's literally just water, or we suspend the virus in the cell culture medium. That's the condition most people use when they determine the UV dosage for disinfections. So we observe that completely two different dosage. If you look at it, if we suspended the virus SARS-CoV-2 in the water, the PBS buffer, they require more energy, less energy. Basically, this is the less energy in order to completely eradicating the virus. If we suspended the virus in the cell culture medium, then we need basically high energy and in order to completely eradicate the virus contaminated the surface. So then we ask the question, what factors play the critical role in disinfections? So we came up with the hypothesis. We basically say it's the medium in which the virus are suspended. That's played a major role. Basically, it's the medium attenuated UVC light and reducing the disinfection efficiencies. So in order to find out whether this is the case, so we designed experiments and we used the model system. Now, instead of using the SARS-CoV-2, we used another retrovirus. Basically, it's a GFP expression retrovirus. Then we can, by detecting the GFP, green fluorescence X protein in the infected cells, then we can count how efficient the virus infected the cells before and after UVC disinfections. Then we can use the automated system. We have a high content imaging system. We can use the automated high content imaging. We'll be able to very precisely quantify the reduction of the virus infectivities before and after UVC infections. We examined, used the 3 different wavelengths. We used the low wavelengths, 222 nanometers. We used the 254 nanometers UVC and 265 nanometers. So 254 nanometers, that's the UVC light most of people use even before the pandemic to disinfect the any microorganism contaminated surface. The problem for 254 nanometers because it generates ozone. That's the chemicals have the very odd smell, and also if they reach the high concentration, it's quite a toxic. Then people discover 222 nanometers UVC wavelengths, they do not generate the ozone and much safer, but also cause the damage to the human skin. So the reason we tested 265 nanometers because most LED UVC light bulb and emit the UVC light at 65 nanometers. So we know to compare the 254 nanometers, so LED is more energy efficient. And that's the reason we try to see what is the efficiency of the disinfection of the UVC light and the different wavelengths. So again, we test the two different conditions. We suspended the virus in the cell culture medium and in the DPPS, that's basically this water. So what do we discover? We discover and the UVC light was attenuated significantly in the cell culture medium. If you look at here, this is the PBS buffer, this is the PBS buffer, this is basically is the cell culture medium. Now we try to find out what is the major component which the chemicals attenuate the UVC light most. So then we check the, because all the cell culture medium, the major component of cell culture medium is the vitamin and also the amino acid and serum. So we discovered the serum, this is here, PBS, that's the FBS, that's a serum. So serum does not attenuate the UVC very much. So it is the amino acid and also the vitamin and attenuate the UVC most. So we screening the a number of the amino acid, also the a number of the vitamin. So we discover it's basically tryptophan and also tyrosine. There's two amino acid absorbed UVC light most, and also one of the niacinamide, and that's the vitamin, and absorb the UVC light most. So what does this discovery tells us? There is a potential we can use those amino acid and also the vitamin to develop the UVC blockers, because remember I mentioned to you, one is the danger of the UVC light is to damage the human skins. That's why the disinfection cannot be performed in the presence of the humans. It has to be in the empty space. Human has to be relieved from the room before you can turn on a UVC light to disinfect the surface. So this basically tells us there's potential to develop the UVC block and use this two amino acid mixed with the two amino acid with the vitamin. So we'll be able to develop the blockers can reduce the damage of the UVC on the skin. Now, the other study, we try to understand to what extent the different cell culture medium on the medium where the virus suspended really affected the UVC efficiencies. We look at the salivas. The reason we look at the saliva because most of the virus aerosolized usually is in salivas, because when you breathe out the virus basically suspended in the salivas. So it's very important to understand how efficient the UVC light can disinfect, eradicating on the virus when they suspend in the salivas. So this is the results, and you can see when a virus is sustained in the salivas, particularly in the short wavelengths, and they are very easy to disinfect it, because this is show you the 3 logger on reduction of the virus infectivities after UVC disinfections. So when they suspended in the cell culture medium, and they usually very difficult to be less efficient and be disinfected. So that's basically is another indication, another bit observation we made through this project. We determined, saliva actually can attenuate attenuate the UVC light. That means in order to completely eradicate the virus, we need to use more energy and more high intensities. And we also detected the environment. So basically light paths, because we know the deeper and the light penetrates and reach to the surface reach to the virus contaminated surface, the less efficient and UVC can cure eradicating the virus. So then we detected what is the relationship between the light paths and also UVC efficient. And this is the data and we show you the result. It's very clear. So the deeper and the light paths, and then less efficient on the virus infections. So this is basically, and then based on those study, we developed the model system. And what this model system is used for is now we have a system, we have a model, and the system can be used for anybody who wants to determine the UVC dosage required for eradicating the virus surface. And the model system can be used by the industry, and they can use this model system to design their devices. And also the model system can be used by the agencies if they want to regulate the UVC products on the market. So that's basically the conclusion we draw from this study. Now we know what affected the UVC efficiency and what the design criteria we need to follow when we design the system and to determine the UVC dosage for eradicating the virus, particularly SARS-CoV-2, and to reach the completely disinfection and virus contaminated surface. Thank you for listening.
Thank you very much, Kaiming, for this wonderful presentation. Again, to the audience, if you have any questions, please share them in the chat. And at the end of the presentations, we're going to have a Q&A section. Now, I would like to invite Murad, who is returning for a second time to provide some updates about his talk. So Murad, you're welcome to begin your talk.
Thank you so much for inviting me back. So when we gave the first talk, we had just started this rapid project. Now we are going to concluding it soon. So I'm happy to be able to have, the record of what were our visions and what we have done. So I'm going to talk about a specific work that came out of this rapid project on how to share public data, public health data, while preserving privacy during pandemic. So it's clear that sharing surveillance data for data-driven response is very, very important. We use data for understanding how transmission happens. The data is used for simulating different interventions, what their impact would be. And also, of course, in many cases, and for future pandemics, we will be needing it to detect outbreaks early on. Now, the question is that whether we can directly share this data, especially whether we can directly share individual patient-level data, which would be useful for building different models. During the coronavirus crisis, we had also have some kind of data crisis in the sense organizations were reluctant to share it, and they were concerned about privacy, rightfully so. And this required them to carefully and in a time-consuming way analyzing which data to be to share it in what format and how can it be made public for future use. So, and this is and one of the compounding challenges is that unlike traditional data sharing settings, we have a data set size that's changing every day because every day we may have new patients can be diagnosed, and these new patients' data may need to be shared. And also for regulation purposes, there are additional challenges for if you do HIPAA compliance, which is the privacy legislation that governs healthcare data. So some people are very comfortable with HIPAA safe harbor rules, which guarantees some certain regular way to sanitize data, but the dates are not allowed, and then this creates challenges for some of these end users. And of course, due to the emergence of the situation, we have to do this very fast. We have to share the data fast without really violating privacy. So in a sense, we developed a framework where we can adapt to these number of records, number of patient records that are changing every day, and we can prioritize different specific information. Let's say you want it to be more detailed with respect to age, but not less race, or maybe you want it to be more detailed on race, etc., while understanding privacy implications. So we developed this risk estimation, privacy risk estimation framework. And the first part of it is that we looked into data generalization. In this work, we focused on the tools where we share the actual correct data that's being given, but at a less specified level or more generalized level. So what does marginalization mean is that, for example, in our framework, for privacy reasons, instead of sharing someone's age, you may share the age range, like it says 5 to 10. Or you can, if you want to protect privacy even more, you can share a higher range, and it may go up to the top where you don't share any information. Of course, the leaf nodes are very precise, but more privacy, potential privacy issues, so less privacy protection. And when we go higher up, less information, but more privacy protection. So the second thing is that in order to estimate the risks, we really look into the population distribution in different counties, and whether, especially for the risk we estimate in this work called re-identification risk. In other words, an attacker who knows some information about the patients, can they re-identify in the data and know that, oh, this record must belong to Murat, or this record must belong to John. So in order to do this estimation, we look at the census data and use the population distribution to identify it. The next setting is that once we get this data, the time series cases, like how many cases reported, the privacy risk metric, we will be using a specific one, which I will describe in a second. And also how often, which we call window of size, how often we would like to share the patient records. We created this Monte Carlo simulation framework where we randomly select the population, we estimate the risk, and we do this thousands of times to estimate look at the risks. And here we look at something called PK11 risk, and we want it to be less than 1%, which means that the percentage of records falling into demographic group of size 10 or smaller should be less than or equal to 1%. In other words, we are estimating that less than 1% of the population would be in a group of patients less than total size 11, or less than 10 other records. So given this risk estimation, and this is kind of based on what CDC is using, so we try to look into that risk basically used by CDC. And we look at the distribution, and based on these distributions, we evaluate the privacy risk thresholds and the policies. So in the experiments next I'm going to show, we use this PK11 risk that I mentioned. We run the simulations for 1,000 times, and we look into 96 alternative policies. And we do this across the counties, and we do this for each country by size and the number of cases. So what we get is that for small counties, when the epidemic starts and we have few cases, privacy risks are much higher than the accepted threshold we mentioned. So you can't really share any data. But as the time progresses, even in small counties, you won't be able to share much, but in bigger ones, at least from this risk point of view, you could have many policies. For example, this diagram says that if the county is between 1 to 50,000 range, and we hit the total 5,000 cases, we would be able to find among the 96 policies we looked at, we would get 31 to satisfy the risk. And these policies are listed, some of them here, like how fine-grained we share the age, whether we had sex, nationality, race, and so on. In addition to that, we look into dynamic policy change. In other words, we don't stick to sharing one type of data, but we evolve what we share all the time. And we compare this with also CDC static policies. In the CDC's case, it divides the age into 0, 9, 10 to 19, and so on, these kind of intervals, like 10-year intervals. It has combined race and ethnicity, gender, state of residence, and county of residence, and date of birth specimen collection. So that's the CDC static policy in terms of data sanitization that's used. Here, we looked at whether our dynamic policy, which adapted based on the risk, could perform better, especially for we do daily and weekly releases basically. So I won't go into all the details, but what happens is that static policies in most of the cases, whether it's a small county or a big county, turn out to have more number of releases where the privacy risk threshold is exceeded. So for example, when we look at the 95% quantified for a small county with population size less than 1,000, we would be having, for the period we look at, we would have 22 days that the risk is above the threshold. This is daily releases. But for dynamic policy, we had even 0. And of course, for 1 million, again, you see the same threshold. So this kind of showed that one policy about data release and what the format it is may not be good. And we need to really adjust as the pandemic evolves. So in this study, what we try to show you is that our dynamic privacy risk assessment framework can give much better results in terms of estimating privacy risks, and it can really adapt to changing environments, which protect with better privacy and utility options. But of course, this work that now we are continuing only look at the privacy risk. We didn't look into what's the different utility of these policies. In other words, in some scenarios for a given acceptable privacy risk, we have 40 different policies. But given the tasks, which policy is better, for example, for outbreak detection, or which policy is better for understanding whether outbreak happening in some race, for example. So we didn't really look into those very carefully. So I will stop here. Again, I would like to thank NSF for supporting us. And this is a joint work with Vanderbilt Medical School and also a colleague from IBM. And what I presented in a very short amount of time, if you want more details, is published at Journal of American Medical Informatics Association just recently. So I'll stop here, and then towards the end, if there are any questions, I will answer live online. Thank you.
Thank you very much, Murad. This is a great presentation as well about privacy and security. So we're really happy to have you today. Next, I would like to move on to invite Zachary Boyd to do his presentation.
Okay. Yes, thanks everyone else for your presentations. It's a pleasure today to share my results on structure and dynamics of global supply chain networks. So unlike the previous projects, this is a 2-year NSF project that we have had some prior work for, but so far we're 3 months into the official project. And I, as a mathematician, I'm doing things that are a little bit more theoretical compared to the previous speakers, but I still think that, you know, we're answering interesting questions and welcome to collaborative ideas at this point, since we're earlier in the project so far. I'd also like to acknowledge my great collaborators, Kayvon Lavasani, who's in a business school at North Carolina Central University, and has helped ground a lot of the questions that we're asking and make sure they're consistent with real actual business sense. And then my student, Jason Vasquez, who's done a lot of great work with us too. So the major goal of this project is to increase understanding of breakdown and recovery of global supply chains, particularly in light of the COVID pandemic. While everyone knows that COVID has adversely affected our supply chains, how to model this change is much less understood, particularly as the challenges are multifaceted and change in time. For example, in the early days of the pandemic, we faced an urgent need for items such as masks and ventilators in unprecedented numbers. As the crisis wore on, we began to focus more on general supply chain difficulties, such as the limited or unpredictable availability of everyday items. In the coming years, it seems clear that supply chain professionals are planning a radical reorganization of their supply chains to try to mitigate the risk of future events like this. For example, by including more domestic-based production or intentionally placing production in multiple foreign locations in case of localized problems. Of course, much has already been known about global supply chains before the pandemic. The problem is that existing knowledge is not well adapted to this kind of a situation. For example, firms in recent years have made fabulous gains in predicting short-term demand fluctuations and optimizing for cost, for example. On the macro level, economists and complexity scientists have mapped out and traced shock propagation through the network dependencies between countries and industries. And finally, following the 2008 financial crisis, notions of systemic risk in finance have been very well developed. What is less understood is and that's needed for COVID, is an understanding of how supply chains can recover as a system. after heavy disruption. No single firm currently has the capability or data to answer this question because of their focus on their own more localized needs, or at least needs specific to their firm. Indeed, it is even unclear what policy actions are available that might help with the problems that we're facing. A particular weakness of the existing knowledge base is that most relevant modeling is about small week-to-week demand forecasting under regular life fluctuations, as opposed to the high intensity disruptions that COVID has caused and that continue to change. My project is in part about developing notions of systemic risk grounded in the patterns of dependency between actual firms, so that we can start to understand what tools we need to ask this question, what data would be useful, and what actions could plausibly be helpful. So I'll describe the major data source that we found the most useful so far. We've collected the largest global supply chain map in existence as far as we know, and are analyzing it. Public firms all over the world are required to disclose their major suppliers and customers, which we've used to glue together our map. While we may imagine a supply chain as being a tiered structure, as in this visualization, once you get to the global level of many intertwined supply chains with many firms, the complex dependencies really yield a tangled soup of connections, as visualized in part here for the auto industry. Note that there are some dominant firms. I've sized the nodes by what we call their centrality, and many, many less central ones that actually get so small that you kind of can't see them in this visualization. We've colored the nodes using community detection, which highlights that there are business ecosystems that fundamentally depend on each other and work in the same space as each other. These ecosystems also do have something to do with geographic distributions. If you look at some of the names, you'll see a blue blob that contains, for example, Toyota, which is separate from some of these green firms, which include the Chrysler supply chain. And so there's certainly some geographic structure in these large extended supply chains as well. So far, we've succeeded a fair amount in just modeling disruption in this network. And the way that we've focused so far is just looking at the long or short-term deactivation or diminished activity of some firms. So from a graph theory perspective, this means node deletion. In some simulations, we did random deletion, which kind of corresponds to widespread indiscriminate destruction. In others, we are trying to actively target large and central firms, which is an attempt to get a kind of a worst case scenario. We've also varied how many firms were subject to disruption, as well as modeling some specific scenarios, such as the cessation of global international trade for a brief time, or a US-China specific trade disruption. Some of our models have also included this idea of cascading failure, which is this important supply chain idea that if one firm fails in the short term or otherwise has to reduce its operations due to outbreak, some firms that it supplies will also have to reduce their operations or shut down in the near term. To measure the overall effect of these disruptions, we used a path counting metric, which captures the idea that resources need to be able to flow vertically up or down the supply chain from distant supply chain connections, like in the bottom of this figure, representing basically kind of raw materials, all the way up to critical customer facing firms. We focused on medical suppliers, for example. The outcome that we measured and reported on the most that we found useful was in terms of the percent of these critical paths through the supply chain that were still usable after various kinds of shutdowns. Sometimes the disruptions were such that many of the critical paths remained operational, as in the left figure where we kind of visualize cutting through in such a way that you can still have some vertical paths, whereas other disruptions were in the right place to essentially knock out all of the critical paths and shut down an entire critical industry in the near term. An example of the sorts of results that we get from this sort of analysis are listed on this page. So for example, if we make the sunny assumption that cascading failure is negligible, so firms can shut down, but this doesn't necessarily shut down downstream firms directly. In this case, the global supply chain looks surprisingly robust to short-term unavailability of randomized firms. So for example, up to 27% of firms could randomly fail before 80% of medical suppliers were paralyzed, or in other words, unable to get things that they needed. In contrast, the worst case scenario, where very central or large firms fail, was much worse. Only 3% of targeted firms needed to fail before 80% of medical suppliers were paralyzed. There were also some key industry country pairs, such as US or China biotech, that were especially critical for the medical suppliers. If instead we assume a strict cascading rule, which is more pessimistic, 25% of firms actually end up having the property that if they are removed, at least 10,000 other firms become inoperable in the short term until they can establish new relationships or the original firm comes back online. And so a failure of one of these firms will paralyze all medical supply firms in the short term. The reality of the situation is likely somewhere in between these two scenarios, and we're working on the parameter estimation problem of how much cascading is really realistic for scenarios that we care about. As a last example, we looked at the US military supply chains, which historically have tried very hard to protect themselves against intervention. And we posed the question of how much risk mitigation is really possible by protecting only, for example, domestic or treaty partner firms through government action. We found that without cascading, some protection really is possible, but when you include a significant chance of cascading failure, then problems in non-treaty countries can quickly have devastating effects in the larger supply chain, regardless of your own individual actions. Okay, so our simulations, no matter how complex, will never be as sophisticated as real life is. Here are some key directions that I see coming up next for us and possibly for others to expand our understanding further and eventually help with supply chain recovery and understanding what the future can hold if we act a certain way. So first, we need to integrate the multiple layers or perspectives of supply chain. This is especially critical when we talk about the transportation layer, which in recent months has been more of a problem than firm shutdowns. So these are two different networks, right? You have a firm interdependence network, and you also have a transport network that need to be integrated. Second, we need to understand what actions are most helpful to get a supply chain network to transition back from low operating capacity to high. And then we need the right measures of various aspects of disruption from real life scenarios like COVID or Suez Canal blockage, the conflict in Ukraine, and so forth. And these will happen on various timescales, and these inform the real decisions that supply chain experts are trying to make at this time to understand how to reorganize the world, basically, to be prepared for the future and provide less risk for all of us. So thank you for your time. I'll answer the chat questions, and I'm also happy to talk over email about collaboration possibilities. Thank you.
Thank you very much, Zachary, for your excellent presentation. Again, to the audience, share your questions in the chat. And before we begin our Q&A section, I would like to briefly make a few announcements. First, I would like to thank all the researchers who have shared their work with us today. If of your presentations provided some unique insights into the latest COVID-19 research, and we appreciate your contributions to the study of this subject. For the audience, let me say that each of our speakers' presentations will be made available in the website covidinformationcommons.net and the Hub YouTube channel later next week. We also gonna be posting the individual talks of the researchers, so you're gonna have access to each talk in particular if you're interested in that. And as we noted earlier today, those presentations will be giving additional accessibility features, including English and Spanish transcripts. So let me just quickly share my screen, because I would also like to announce our next webinar, which is scheduled for May 5th at 2:30 p.m. Eastern Time. You're welcome to register. We have all this information on the website. This webinar is going to focus on behavioral and social sciences during the COVID-19 pandemic. So these amazing scientists will be sharing insights about stress and social distancing and crime and so many of the support and mitigation strategies to help support people during the COVID-19 pandemic. Additionally, we're going to be sharing this in the chat. If you have some time, we'll be happy to have you as a follower on Twitter, on LinkedIn, or interacting with us on the community Slack or sending us emails. So this information will be shared in the chat, so you're welcome to join any of these channels that you are interested in. So finally, I would like to mention that today, once we finish this webinar, you're going to receive a form. It's a quick survey where you're going to be asked a few questions about this webinar or any feedback that you have. So please, we welcome your feedback. So please answer the survey if you have some time. Now, I would like to open it up to the Q&A section from our audience. I saw a few questions popping up in the chat, so thank you for that. So the first question I saw in the chat is actually came from the audience. I see the name here, Santino. Santino, do you want to unmute yourself and ask your question? Or if not, I can also ask the question. Let's see if Santino is here, and
They're here, but it looks like you can ask it.
he's not. Okay, good. So in that matter, so Santino asked a great question. He is asking a question for Justin. So he says, what is the cost effectiveness per region of Shieldnet mesh? Do you have any available data? And what is the effectiveness in reducing healthcare worker infection?
Hey, so I'm not sure I totally understand the question, to be honest with you. Santino, if you're able to give more context, what do you mean by cost effectiveness? So I guess to be clear, oh, maybe there's something in the chat now. To be clear, Shieldnet did not, doesn't cost anything to run. We did not take any revenue ourselves. So there's no cost for Shieldnet itself. Shields were sold at cost in most cases from the manufacturer to suppliers.
If I could guess what they're saying, and Santini can tell me if I'm wrong in the chat. So if you think of how much it would cost somebody to get them on the open market versus working through Shieldnet, what's the cost of effectiveness to the user, like to the end user? Like, were they paying $1,000 per shield, and then with you, it was 90% less? That's how I took it. And is that different by region? Like if you're working with Yemen versus you're working with Texas, is it that your supply chain was totally in the US, so it's not as cost effective to have to ship them there, or it costs them? So I think they're looking for what those different dynamics are of the cost effectiveness of the whole process. That's from my business background, that's how I would look at it. But
I see. Then I would answer to say that the prices people were paying to procure shields from the Shieldnet program would have been very similar, or perhaps slightly cheaper than what you could have got on the market. Similar in this, that's partly because we asked many of them to sell at cost. Many of them volunteered to sell at cost. I do know that there were other platforms operating during the pandemic that were doing donations of PPE, right? So potentially you could, I guess, have procured some things through there, which would have definitely been cheaper, but I'm not sure how reliable that is long-term. In terms of effectiveness in reducing infection, I mean, OSHA requires face shields for frontline healthcare workers interacting with COVID patients. It's one of the core components of a PPE, outfit, along with masks and gowns and gloves. So, we know, for example, that healthcare workers without adequate PPE, so those, without wearing some of those components, are at an increased risk of infection, somewhere between 2 and 20-fold, depending on the setting and the country. So hopefully that answers both of those questions.
Well, that's a big number. 2 to 20-fold. 20-fold is rather impressive that you could actually make it that much safer.
I think those would likely be situations where there was potentially some type of aerosol procedure happening, right? So you could imagine if you weren't wearing adequate PPE, but you were intubating a patient, that's you're almost guaranteed to be exposed to particles.
Very interesting. Very interesting. Yeah, and actually, Santino said that was the rationale of the question as we discussed it. So thank you for your flexibility, Justin. It was very thoughtful of you. Kenya, back to you.
Yeah, so thank you very much for that. And Santino, thank you very much for your question. And I have another question for Justin as well. So you were talking in your talk that there's obviously a difference between the conventional supply chain and probably other models that emerged during the COVID-19 pandemic because of what we were facing. And you also said that in comparison, for example, with matches like online dating or job searches, the research that you've been doing show it to be very successful and to show great matches to support the supply and demand change. So my two questions is like, what are the key takeaways that you think is what is making your model a very good model and for supply chain, and what is the difference between what happened with the conventional supply chain and what people are adding now during the pandemic that you think is going to probably prevail after the pandemic?
So are you asking basically like how's the way that we're going to react to the pandemic different from how we were reacting to other previous economic difficulties that we've had before? Yeah, I mean,
yep.
Okay. Yeah, I mean, I think people are still kind of reeling about this and figuring out it's becoming more clear that big changes are going to happen. I think one thing is that people are becoming much more skeptical of these geographically extensive supply chains, right? Where we get pieces assembled, partly in China, partly in Malaysia, partly in South America, and eventually it's supposed to reach you, which is fine under normal times. But it in COVID it becomes clear that these problems occur differentially through space, and then you have to rely on the transportation network to get from one place to another as well. And so there's a big pullback from these geographically extensive supply chains to say maybe we need, at least part of our capabilities to be domestic, for example, or at least to rely on multiple pathways to get to us in case disruptions like this occur. So that's an example of what people are starting to think.
That's a great insight, and I think I'm also linking to something that Zachary mentioned, who has been working on the global supply chain as well. So that comes into me just to ask Zachary as well, like maybe adding some comments to what Justin said about what have been the limitations to maybe partner with global supply chain now that when we were during the pandemic, we had so many restrictions and we were thinking about local and domestic, but then you have been working with the global supply chain. So what do you think have been also the takeaways on the difficulties to partner with international companies or institutions?
So I think Zachary just answered. So I think you meant Justin. Did you want Justin to answer now?
Oh, sorry. Yes, I was originally asking it to Justin. I think.
Sorry, I got my wires crossed on that too. Sorry.
That's
your answer was great.
Yeah.
Yeah.
This is supposed to be
excellent.
collaborative. This is supposed to enable researcher collaboration. So nobody gets to be right all by themselves. We actually get to share our thoughts, which is really great. So thank you for adding your thoughts already, Zachary. Justin.
Oh, sorry. Yeah, Justin.
I guess so. You kind of asked two questions. I mean, I agree with certainly what Zachary was saying. I think, this whole aversion towards large global supply chains was part of the reason why things like Shieldnet were successful, right? Sort of these like local, small scale supply chains is exactly what we were sort of operating in. So that makes sense. I mean, not every product is able to be a part of such a supply chain. So for example, like an N95 mask doesn't really work like this because you need specialized manufacturing, you need approvals from government agencies, whereas a face shield is just some plastic and simple things like that. So gowns, masks, gowns, gloves, face shields, those could be done in a pop-up way, but I don't think these more regulated products could be. We didn't have, I do international work broadly, so I enjoy collaborating with those folks. I think there was lots of appetite for this. People wanted to move quickly. So I didn't see a lot of big challenges in that space, at least nothing unique to the pandemic. I mean, there's always challenges with global research. And then the last thing I'll add is that there are some examples of pop-up supply chains in other disasters out there. So for example, there's companies in the US that operate like pop-up fuel supply chains during disasters. This is common during hurricanes where companies will fly in fuel trucks that have like little pumps on them. So it's like essentially a pop-up gas station. So you kind of see this thing in some other areas.
True.
Yeah.
Yeah, I remember that when I think there were actually companies that were bringing in trucks of fuel for their employees.
Yep.
I think I heard of that, like that they had them in their parking lots or something. And so if they drove to work, they could, fuel up type
And
of
this
thing.
happened
There's an
in Puerto
incentive.
Rico too during Hurricane Harvey,
Yeah.
right? And Hurricane Irma and during that year. Yeah.
Yeah, it makes you wonder what people are really planning. Now that they're all thinking about this and talking about it, and we've been dealing with it for 2 years now. You're always looking, is there toilet paper? Like, I don't know, I have PTSD from toilet paper at this point with COVID, but is it there or not? And it makes you wonder how people are really planning, how companies and governments are really planning, for this integrated supply chain, global supply chain. And even, as they say on the plane, put your own mask on first, now you have to think about that, right? When it comes to a different type of mask, it's not an oxygen mask necessarily, but the PPE and how that flows. And the changing rules of PPE, like even on campus, they said, okay, no cloth masks inside. You have to wear a different one. I'm like, some of those don't look better than cloth masks to me, but it depends. And the standards, I'm not really sure how the standards are done. All the N95s don't look as effective as each other to me. Maybe, it's a non-professional eye, but I don't know. So I think there's a lot of question and uncertainty in the supply chain and the demand chain in general. So it'll be interesting to see how it plays out into the future, what preparation people are doing for risk management, and that how that might evolve along with where they're willing to get things from and how they, spray out, as you said, to try to get multiple locations, local and global. So very interesting discussion. And actually on that note, we're thinking of creating like a working group around supply and demand chains. It could be, related to the pandemic, but it could go broader than that. So we'll be asking the PIs who spoke about it today, and we'll be asking the broader group. And we're thinking that could be an interesting discussion to bring into our inaugural annual KIC workshop that we plan on doing later this year. So hopefully anybody who's here will be invited. We're, open and inclusive in the KIC and all the hub work that we do. So we're thinking that would be interesting so we can continue to discuss this. And as in any good market research, bring in the new data as it comes in, right? And see where we're going, and then look at new, data science tools and techniques we can use for predictive analytics. So I think that would be a lot of fun, and you're nodding your head, so that's a good sign. So Ken, I think we have a good idea.
It is wonderful. I've been thinking about that since I got the confirmation that the speakers wanted to present today. So that's something that we're probably going to be following up in emails about this annual workshop. And just to continue with the Q&A, Benji, who is our Columbia student, he would like to also ask a question that he saw in the chat. So Benji, if you want to do so. Is Benji?
Yeah, his
Yes,
internet was a
yes,
little bumpy, but he's okay now.
Perfect. Okay.
Yeah. So this is the question for Justin. So what is the production cost of one N95 mask, and did the urge of the pandemic lead to any innovations or efficiencies in production that reduce the production cost?
Good question. I don't know the production cost. So we didn't work on N95s much, so I don't know the production cost of N95s. I can give some context to the second one. I'm not sure if there were innovations or efficiencies, but I know, for example, that several producers of N95s have increased their production capacity. So most notably 3M expanded their production capacity here in the United States. Part of that was because of funding from the Defense Production Act from the federal government. But I'm not sure if there were these sort of cool innovations that occurred because of the extra pressure put on them because of the pandemic. Not sure. Maybe one of our other speakers.
Yeah, I think it's the cost is not an issue for N95 maskers. I think it's what's happening in the early pandemic is the interruption of the supply chains because of the pandemic. So that's the huge problem. If we look ahead, prepare the future, another round of the pandemic. Who knows what will happen in 5 years, 10 years, or maybe 2 years from now. So it is the lesson we learned is the supply chain. How do we basically secure the supply chain during the pandemic? So the technology we're talking about here, try to reuse and through the disinfection or any treatment, is to come up with a short solution and to fill the gap why the supply chains is interrupted. And that's basically it's a temporal solution. It's not basically it's permanent solutions.
Very interesting. Kenya, should I ask Murat a question and then we can come back into the PPE and the supply chain just to mix it up a little?
Sure.
So Murat, I'm not an expert on PK11 myself, and I was looking trying to look all the way through the slide when you were talking to figure out what else I knew about it, and there really isn't much there for me. So maybe other people are in the boat with me. So can you explain PK11 a little bit more and how and when it's used in your use case and maybe for other use cases? It looks like it might be a risk management framework that we could all benefit from.
Yeah, I mean, so this is one of the older things actually in understanding privacy risks. In this setting, what you look into is that whenever you share data, imagine attacker knows, you can define, depending on the scenario, like the age, gender, race, and maybe the diagnosis date of the COVID-19 patient. And then your data may have other information, like whether the person passed away or other things. So the question becomes, given this information, can you re-identify the person? So we estimate that risk by looking at if we group the individuals based on age, gender, race, and diagnosis date, do we get at least groups of size 10 or more? And how many people are in a group size 10 or more, which means the total size at least 11. So we want that proportion to be at least 99% of the people to be in a bigger group of size 10. So attacker cannot be able to say that, oh, this is Murat's data, because there are 10 people that will match that profile once we generalize at least 10 more people.
Okay. So,
and we only have for very few people that they would be in a smaller groups, like 3 or 4 people with them. So now attacker's identification could be higher. So that's the PK11 risk. In other words, we look at how big your cohort group with respect to a potential privacy attack. The bigger is better because it's much less likely for you to be re-identified.
That was very helpful. Thank you. So now when I hear it, I'll know what it means. So
Sure.
Thank you very much. And maybe everybody else knew, but I didn't.
It's a very specific privacy target. I don't think so. I just wanted to give high level, so I didn't go into details, but thanks for asking this very good clarification question.
I love learning. I learned so many different things on these webinars, so sure. So Kenya, back to you.
So now that we also, I have a question for Murad. So when you were in your talk, you were explaining about this risk privacy framework that is helping to create policy in public health, in healthcare, to protect data. And I know that healthcare in particular has been very vulnerable during the pandemic because, telemedicine and now so many risks that hospitals or providers were really not aware of. And now suddenly during the pandemic, they were like, oh, wow, what can we do? What are we going to do? We didn't have the systems to protect all of this that is coming up. So my question always when I hear about these issues and about people trying to help to solve a problem did we learn something during the pandemic? Do you think, Murad, that we're actually going to have better frameworks and models coming up? Or because sometimes when we look into history to other pandemics and other disasters, we see that once it ends, we come back to normal again, to the things that probably were not working. So do you think that we have made an impact? Do you think that the scientific community really has changed and revolutionized the privacy and security framework?
I think so. I think there was lots of development happened. So I just talked about one very specific use case where we try to protect privacy while sharing data. But also organizations needed to work remotely and jointly to do things. So it really first, increased adoption of more secure remote tools for like remote work. And also, I think in addition to it, some of the cyber attacks, healthcare organizations realize that they need to improve their posture. Of course, it's not that, I think it's not enough now, so we need to really continue working on it. But I think there is still an improvement happened, and I expect it to continue. But clearly, it's not enough, and I'm sure next pandemic will test different aspects of it. And what we really learn, at least from, I can talk as a computer scientist, IT and data and cyber aspects, having a flexible organization and flexible IT infrastructure that can adapt to the threats, and where you have good backup plans. If something fails, what would you do? If there was a cyber attack, what would you do? If you need to share this data, how quickly you can understand the privacy risk and share it. Mm-hmm. So that flexibility and having that in the organization is critical, of course, combined with the tools available.
That's wonderful. And especially I like the idea of your research of taking all these great insights into policymaking, so that I believe that once you take it to that level, we can really see more impacts in anything that we're doing. So thank you for that, Murad. There is also another question from the chat. Janice, she actually asked the previous question about the N95 mask that Kaiming was answering to, but she also asked another question specifically for Kaiming or any other speaker. She asked, what other viruses do you plan to study with the ultraviolet light? How will you compare the dosage required to break up a virus with the UV dosage humans, that they get on average day? So I guess she's, asking specifically, what other viruses you plan to study with the UV light, and the dosage that sometimes can be dangerous for humans? Like, how do you really manage that and compare that?
Well, this is a good question. For this particular projects, we, obviously focus on the SARS-CoV-2, and the reason we use the retrovirus, because we use this retrovirus as a model virus, allow us to design the devices and to test the devices much easier on the more relaxed conditions, because retrovirus can be worked on the biosafety level 2 environment. And then if we work on the SARS-CoV-2, we have to use a biosafety level 3 facility to carry out all the tests. Our plan in the moving forward, actually, we still continue working on these projects, is to test the efficiency of the UV light on all the airborne and microorganisms, not only the virus, but including all the other microorganisms. Actually, we are right now more focused on using the LED. I mentioned during the presentations, LED more energy efficiency, low cost. And that's the reason we focus on the more LED. We actually just filed a patent and application on the technology we developed. Now, to answer your second question, compare the dosage required for eradicating the virus and compared to the UV dosage of human skin absorbed and every day. So that's two different things, because remember, in the very beginning, I talking about the UV light has a 3 category. One is the UVA, UVB. That's basically long wavelengths of the UV lights and can penetrate through the atmosphere and reach to the human skin. But UVC is more short wavelengths. Basically, they cannot penetrate through the atmosphere. Usually, our human skin are not exposed to the UVC light. So, only the dangers, as to say, if we turn on the UVC light, if any human, the presence of the human, if you expose your human skin to the UVC light, and that's the time we cause the damage. So actually, we did a testing for this particular project. We're using the cadaver on skins to expose the cadaver skins to different wavelengths of the UV lights on a different dosage. And we clearly show the UVC can severely damage the skins, and not only the mechanically cause the crack of the skin, but also we detected the mutation of their genome, basically in the DNA levels. So that's why, in the daily life, you don't worry about the UVC because that light will never reach to the surface of the Earth. They already attenuate when it, pass through the atmosphere.
Thank you. Okay, thank you, Kaiming. And then, so also thank you to Janice for the question. They, she or he, I really don't know who's Janice, to be honest, to acknowledge it. She's in the chat, so I'm not sure if it's she or he, but she also asked another great question. And this question is for Zachary or any other speakers. She asked, or she or he, asked that the supply chain disruptions.
Yeah, I'm sure other people on this call can also attest that some prices have changed really wildly. If you've tried to buy a car recently, for example, the prices have gone through the roof. Sometimes cheaper to buy new, but other things have proven to be more sticky, right? I mean, there's always this economic option of you can raise the prices and allocate goods to the people who have money to pay for them, or you can keep the prices more close to fixed because of either social expectations or legal requirements not to gouge or things like that. And in that case, you end up with a shortage, and it's kind of a different allocation problem than people wait in long lines or other things like that. But absolutely, the prices have responded to what's happening right now.
Okay, thank you for that, Zachary. And again, I'm acknowledging I really don't know who's Janice. She's with us, and we are grateful to have her or he here with us. So, Florence, do you have any other questions that you would like to ask to the speakers?
No, I was just looking. There was a more detailed Yanis. And so I saw, Murad, I don't know if you answered the question that Yanis asked.
Actually, I was typing. I have to leave in 2 minutes.
Okay.
So I was typing an answer for Yanis. Let me just answer online.
Okay.
Basically, Yanis was asking about longitudinal studies, and she has a very good point that you want to follow the patient. There, the care must be taken in the sense that while you are disclosing information, if you disclose something in the past and you again disclose something with that patient slightly differently, it may cause an attacker to re-identify the patient. So our framework can be adapted, but longitudinal studies make things a little bit challenging. So you need to really make sure that you are consistent in what you are releasing and need to consider what you released in the past, basically. But it's doable.
Perfect. So thank you for that, Murad. And finally, I have a quick question for Kaiming before we close today. So I found many UV lights products online to clean my phone, to clean, I don't know how, so many things. Do you think, what do you think are the quality standards that I, as a user, or many other people should look at and say, hey, this UV light is good or not, based on the model that you have been replicating in your research?
Well, I think this is a very excellent question. This is excellent questions because this is the confusion we try to clean up through these studies. Because in the very early on, even a lot of people, when the people talking about a UVC disinfections, and suddenly you see the almost many products are sold on the Amazons. And you're talking about people get those very small UVC devices, can use for sterilize the iPhone, sterilize the envelope, and sterilize any shopping bag when you brought back from the grocery shop. The one of the confusions, when also we receive a lot of call from the ordinary people, from the customer, from the communities. They ask whether those devices are safe for, number one, is safe for use. Number two, whether this device is efficient and to be able to completely eradicating the virus. And we look at the description, we call the company, and all the answer we received, basically, they think it will work. So there's no scientific evidence to back up those claims and back up their product descriptions. And because there is no standard exist for regulating these products. So the reason we contacted the FDA, we contacted the EPA, and we contacted the NIST and asked why there's no such a standards. The answer we received, because no scientific data there's no such data exist in the literature, and in order to do that. So the study, that's the reason we set out and start to ask a scientific question, design a system, develop the model system. That model system and will allow the industry to use when they design the products to answer the question, what is the dosage required? What is the energy efficiency? And how the system should be configured in order to deliver the efficiency as expected. So that's basically the contribution we made through this program, and provide a model system and provide the methodology, a protocol, allow people to standardize, because one of the confusion we also look at and find in very early on whereby examining the literatures, because a lot of people talking about and you see there is a variety of the dosage report in the literatures. And then we've set up, we try to duplicate the experiments, and that's the reason we developed the system. We developed the methodology to standardize the determination of the dose required for UVC to work properly. And by using the system, that everybody, when you use the system to determine the dosage, no matter where you are, and on the company A, company B, the lab A, lab B, the dosage will come with the same dosage if using it standardized. So that's basically what we try to do.
It's so interesting listening to you, Kaiming. We've had a number of researchers present on this topic of, decontamination or, whatever of the masks and PPE. Kenya, I'm wondering if this would be another interesting little working group or like a meeting to have where they could share their research, and maybe we can make it like a project for a couple of students to do like a little literature review and an analysis on. It would be cool if out of this COVID Info Commons and our research collaboration, we came out with some papers or reports or something. Correct. So that we can have the documented views, different perspectives is always valuable, as you know, okay, I can hear you saying that, and to compare them. So when someone doesn't see one report, they say this is it, but that they realize there's a range of how this could be done and what some of the most effective ways are. That could be a lot of fun to do. What do you think about that?
Yeah, I think you're absolutely correct, because this is a very, very critical and very important particularly we're talking about the effectiveness of the devices, right? People design out many devices. If they don't know what the standard they should follow, now we screw up. We will screw up everything.
Absolutely. And there's UV, and there's heat, and there's microwave, and there's chemicals. There are all these different options I've heard. Different
methodologies people use it. But the question is whether those data compatible. So you methodology design in the lab A and the lab B, and they tell you there's a different thing. And many times the reason tell you different things because they didn't standardize. So I think yes, I would be very happy to.
That would be great. Let's talk about that. Yes. Kenya, I know this is one of your ideas about creating working groups, and being researchers, we know that we do things differently. There's not going to be a standard. We're not using all the same clean room to do this at the same time. There are different environments we're doing it in and different techniques we're using. So I think that would be very interesting. And maybe we could make that one of the projects for our real volunteers. So we have a volunteer program through the Northeast Hub, and working with the COVID Info Commons is one of the opportunities. And it's the Real Volunteer Program. It stands for Research Experience and Leadership Opportunities for Students.
Yeah.
And maybe this would be a cool thing to create a little group around to see if we could get a couple of students, undergrad, grad, community college, we're flexible. That would be fun, wouldn't it?
That would be fantastic.
Let's see if we can do that. We also have high school students. I love young, brilliant people because they're going to be older, brilliant people soon. Yeah. So let's get them involved.
Let's talk about it.
That sounds great. We'll definitely do that. So Kenya, if you could get us together and we can get the ball rolling, and then we can reach out to some of the other PIs because they've already, a number of them have presented, because I've listened to this story from different angles now over the last few years.
Excellent.